Hello, everyone, and welcome to the Worksheet 9 video key. All right, Worksheet 9 is on stereochemistry part 2, and we start off with the first part of how to assign RNS configurations on an asymmetric carbon. So it talks about using atomic numbers, prioritize the 4 groups attached to the chirality center as 1, 2, 3, and 4. The next step will be to arrange the molecule in space so that the 4th priority group faces away from you. When you go from 1 to 2 to 3, if that's a clockwise rotation, it's R, and counterclockwise would be S. So for example, we have 2 enantiomers drawn here. You can tell they're enantiomers because we've just switched the chlorine and the methyl and left the OH and the hydrogen the same. You can see that they're drawn on opposite sides, but the OH is still on a wedge and the hydrogen is still on a dash. So the only ones that have been changed are the chlorine and the methyl. So that should generate the enantiomer. And the groups have been assigned by atomic number. Chlorine has the highest atomic number, followed by oxygen, followed by carbon, and followed by hydrogen. In this case, because 4 is pointed back, we can just do a 1 to 2 to 3 rotation. Clockwise is R. And 1 to 2 to 3 in this direction would be counterclockwise and S. So let's use that knowledge to assign the RNS configuration on the following asymmetric carbons. So the first step is to assign the priorities 1, 2, 3, and 4 based on atomic number. Bromine has the highest atomic number, followed by chlorine, followed by fluorine, and lastly, hydrogen. We notice that we have a 1 to 2 to 3 clockwise rotation, so this is R. We can do that because the hydrogen is the 4th priority group and it's pointed back. We have the same situation here. The hydrogen will be our 4th priority group and it's pointed back. So we'll be able to do a straightforward clockwise or counterclockwise rotation after we figure out the priorities. Fluorine has the highest atomic number, followed by oxygen, followed by carbon, followed by hydrogen. And again, I just go from 1 to 2 to 3 with the 4th priority pointed back. This is counterclockwise and S. Let's do priorities over here. We have oxygen, nitrogen, then carbon, then hydrogen. With the 4th priority back, again, I can do 1 to 2 to 3. That's a counterclockwise rotation and S. Let's look at the priorities over here. Bromine would be first, followed by sulfur, followed by oxygen, followed by carbon. Notice there is not a hydrogen attached to this carbon, and that's okay. There isn't always a hydrogen. It's common, but there's not always one. The important point is that the 4th priority group is pointed back. If that's the case, I can go from 1 to 2 to 3, and this is a counterclockwise rotation, and this is S. Now we're looking at a Fisher projection. We just need to recall that in a Fisher projection, the groups on the horizontal are coming out at us, and the groups on the vertical are pointed back. So with our priorities, we have bromine, chlorine, carbon, hydrogen. Even on a Fisher projection, we can just do a straightforward 1 to 2 to 3. With 4 pointed back, this will be clockwise and R. Same thing here. These are coming out at us. These are pointed back. Let's identify the priorities. Sulfur, followed by oxygen, followed by carbon, followed by hydrogen. And again, we have a 1 to 2 to 3 clockwise rotation. So this one is also R. Here's a little reminder that when atoms on a chiral center are the same, analyze the atomic number 1 layer at a time. So oxygen will clearly be the 1st priority and hydrogen will be the 4th, but this carbon is a tie with that carbon because they're both carbon. Then we have to look at what are these carbons attached to. On the left, we have carbon, hydrogen, hydrogen, written here, and then carbon, carbon, hydrogen, written there. And then the second attachment is the point of difference, carbon being a higher atomic number than hydrogen, and therefore the carbon on the right has a higher priority than the carbon on the left. With the fourth priority pointed back, we can just do a 1 to 2 to 3 clockwise rotation, and this is R. Looking at the next one, assign R and S configurations to the following asymmetric carbons. So here we have oxygen, oxygen, carbon, hydrogen. Well, this is definitely going to be priority 4, and carbon will definitely be priority 3, but oxygen and oxygen are a tie. Then we look and see what are they attached to. This one's attached to carbon, and this one's attached to carbon, so that's a tie. But then we have hydrogen, hydrogen, hydrogen versus carbon, hydrogen, hydrogen. This is going to be priority 1 and priority 2. So we do a 1 to 2 to 3 rotation with the hydrogen pointing back, clockwise is R. Coming over here, we have carbon, 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 hydrogen. So this is the only one we know for sure, and the other ones are all a tie. Between them, though, we can see that this carbon is attached to carbon, carbon, carbon. This one is carbon, carbon, hydrogen, and hydrogen, hydrogen, hydrogen. This is 1, 2, and 3. With the hydrogen fourth priority pointed back, 1 to 2 to 3, clockwise, and R. Moving on, we have this carbon, which is asymmetric. We have carbon, 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 hydrogen. Again, all 3 carbons are a tie, but hydrogen is definitely last priority. Looking and seeing what's attached, this one has hydrogen, hydrogen, hydrogen. This one is oxygen, hydrogen, hydrogen, and sulfur, hydrogen, hydrogen. Sulfur has a higher priority than oxygen. So this is 1, 2, and 3. Again, 1 to 2 to 3 with the fourth priority pointed back. This is counterclockwise and S. Coming back over here, we have a carbon attached to carbon, carbon, oxygen, hydrogen. Oxygen is 1, hydrogen will be number 4, but carbon and carbon are a tie. This carbon is attached 3 times to nitrogen. This is only nitrogen, hydrogen, hydrogen. This one will have the highest priority, and we'll give that one priority number 2. With the fourth priority pointed back, we go from 1 to 2 to 3, clockwise, and R. Coming over here, we have bromine, carbon, carbon, hydrogen. Bromine is 1, hydrogen is 4, carbon and carbon is a tie. This carbon is attached to 3 hydrogens. This one is attached to carbon, carbon, hydrogen. This is definitely 2 and priority 3. 1 to 2 to 3. That is counterclockwise and S. Moving over here, we have carbon, 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 hydrogen. So the only one we know for sure is number 4. The rest are a tie. And then attached to this carbon, we have hydrogen, hydrogen, hydrogen. This one is oxygen, hydrogen, hydrogen. And this one is carbon, hydrogen, hydrogen. So you might have been distracted by this bromine, but it's too far away, and we have to go in order of atoms attached. So oxygen beats carbon, which beats hydrogen, and this gives us our priority of 1 to 2 to 3, and then a 1 to 2 to 3, and counterclockwise rotation is S. Moving right along. Now it starts to talk about what do we do when the fourth priority group is not behind the plane of the page on a dash. Well, there's a variety of strategies you can do. One is to swap two groups to make it dashed. And you could optionally also swap the other two groups a second time to generate the original structure. And then it says, pro tip, do not redraw the entire molecule, only redraw the numbers. All right, so we can do that. Let's first identify the priorities. We have bromine first, chlorine, then hydrogen, which somehow got an F instead of a number 4. And we notice that our fourth priority group is not behind the plane of the page like we want it to be. So what we can do is do some switching. We will switch the fourth priority group with what is currently behind, which is the bromine. And we can also switch the fluorine and the chlorine simultaneously so that whatever we figure out will be the same configuration as the original structure. So redrawing it, we're going to use our pro tip and just do 1, 2, 3, and 4. So recall that we switched 1 and 4. This is going to be 4 and this is going to be 1. And we switched 2 and 3. So 3 will be here and 2 will be there. So now we can do our rotation, 1 to 2 to 3. This is clockwise and R, which means that this one is also R. Let's look at the next structure. We're going to assign priorities. Fluorine is first, oxygen is second, then carbon, then the hydrogen. Right now, our third priority group is going back, but we want our fourth priority group going back. We are going to switch the fourth priority group with whatever is in the back, which is a methyl, and we'll switch the other two as well. We can redraw it. We'll just draw it exactly like we see it, except with just the numbers. And making sure to do the switches that we had talked about previously. So again, we've switched 3 and 4. So this is now 4 and that's 3. And then we've switched 1 and 2. So this is 1 and that's 2. Again, we need to do 1 to 2 to 3. Fourth priority is pointed back. This is counterclockwise, and S, which means this one is also S. Maybe I'll circle them so that's more clear exactly what it is. All right, moving on to the next one, let's look at priorities. Oxygen has the highest atomic number, followed by nitrogen, followed by carbon, followed by hydrogen. Right now, our first priority group is pointed back, but we want the fourth priority group to be pointed back. So we'll switch those two and simultaneously switch the other two as well. Go ahead and redraw it. Making sure to put in the new priority groups after the switches. So this is now going to be 4 and this is 1. And this will be 2 and 3. So again, 1 to 2 to 3. The fourth priority group pointed back. This is counterclockwise and S, which means this one is also S. All right, let's look at this structure that's drawn using a Fisher projection. So again, I can redraw this. And I can draw the carbon, the two wedges, the chlorine and hydrogen, and then the dashes to the bromine and methyl. Let's go ahead and assign the priorities. So the priorities are bromine is first, followed by chlorine, followed by carbon, followed by hydrogen. And then we have to look and see, oh, my fourth priority group is not currently pointed back. Instead, it's pointed out at me. So one thing I can do is some switching. And I want to switch it to the back. And either one of these would be switching it to the back. So you choose. Let's go ahead and switch it with the bromine. And we also have to switch the other two groups. So when we redraw, what we end up with is a carbon and then we'll put in our priority groups. We'll do 1 here, 4 here, 2 here, and here. We have 1 to 2 to 3, that's counterclockwise and S, which means this one is also S. Moving on, we have the next structure. And looking at priorities, we have carbon, 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 hydrogen. All the carbons are tied, but we can look and see what they're attached to. What we'll end up with is the propyl being first priority, ethyl being second, and methyl being third. And we can redraw this. After doing some switching. Because currently my fourth priority is coming out at me and I want it to be behind. So I'll switch those two and switch the others as well. After the switch, I will end up with 4 and 3 and 1 and 2. And then 1 to 2 to 3. This is a clockwise plus R rotation, so this one is also R. And then lastly, this one has 2 different stereocenters to figure out. So no problem, we can just treat each one separately. The priorities for this carbon are, we have oxygen, carbon, carbon, hydrogen. This will be 1, that will be 4. And then this carbon and this carbon are a tie, but this one is attached to sulfur. It will be priority 2 and 3. Luckily, this one is drawn with the hydrogen going back. So it's a pretty straightforward. Clockwise is our analysis. And then for the other one, we have sulfur, carbon, carbon, hydrogen. So sulfur is priority 1, hydrogen is priority 4. These are a tie, but this one will end up being 2 and 3. So we're going to use a different color here. We're going to do 1 to 2 to 3, which is a counterclockwise in S, but look at the hydrogen, it's coming out at us, not pointed back. So this is actually also R. I just used a trick where instead of redrawing it, I noticed that my fourth priority is coming out at me. So when it looks like a counterclockwise rotation, I can actually change it to a clockwise rotation. And that only works if the fourth priority is coming out instead of pointed back. You could also do the redrawing and come up with the same answer. Looking at the next one, it says RNS configuration is indicated at the beginning of a compound's name in parentheses. Name the following according to IUPAC system of nomenclature. So we just want to name it like we did before, but add the R and the S. So I'm just going to redraw it so I don't get confused. And I'm going to have the carbon with the wedge, the dash, and the 2 other groups that are in the plane. And I'm going to go ahead and put the priorities over on here. So we have carbon, 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 hydrogen. So this is definitely priority 4. And then this will be priority 1, 2, and 3, based on what I'm seeing over here. So we have 1 to 2 to 3, which is a clockwise and R configuration. So when we put the name together, we'll put R in parentheses first. So let's go ahead and work on the name. So again, we want the longest carbon chain. And we can figure out what that is, right? So we have 1, 2, 3, 4, 5. That looks like the longest carbon chain. So I can assign locants here. Right, so it could be starting in this direction, or I could have started in the opposite direction. Let's go ahead and look at what that would look like. If I had started in the opposite direction, we would have started on one of those 3 carbons, gone to 2, 3, 4, and 5. And then the tiebreaker is getting to the substituent first. So this has a substituent at carbon 2, but this has 2 substituents at carbon 2. So this one is actually going to be the preferred locant numbering system. All right, so then substituents are methyl, 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 and methyl. It looks like there's 4 different methyls. So putting this all together, we have R in parentheses, dash, and there's 4 methyls. So we have 2, comma 2, comma 3, comma 4, tetramethyl. And then the parent, which is pentane. All right, looking at this other one, we want to assign locants. We have 1, 2, 3, 4, 5, 6, 7. And this is the correct direction to get to the lowest number for the first substituent. 1, 2, 3, 4, 5, 6, 7. Right, so most of the name will be, these are 2 substituents. Right, we have 3, 4 dimethyl, and then heptane. But we don't want to forget the R and the S configuration. So we can figure that out. So for carbon number 3, let's say carbon 3, we have 2 groups in the plane, and we have a methyl coming out at us and a hydrogen pointed straight back. Right, so, and I don't want to, I guess I don't want to really put the carbon 3 here. I'm just going to put a little arrow to where I got the 3, because that's not priority 3, that's just carbon 3 on the structure. All right, so for the priorities, let's do those in green. So we have the hydrogen will definitely be priority 4. And then we have the carbon, carbon, carbon. When we do the further analysis, we'll end up with 1, 2, and 3. So 1 to 2 to 3, that's a counterclockwise and S rotation. Right, and then over here, I'm going to do carbon 4. And I'm going to draw the groups attached here. And again, I'm going to make a little line so you know exactly why I've drawn C4. And then in terms of priorities, right, we know the hydrogen will be the 4th priority. And then we have methyl, and then the 2 carbons in this direction. We'll do 1, 2, and 3. We can do 1 to 2 to 3. And again, this is counterclockwise and also S. Except for, oops, we forgot, the 4th priority group is coming out at us and not pointing back. So instead, we have R in this case. Because again, we're going to switch it because the 4th priority group is not in the direction that we want. All right, so putting that all together, these will be part of the name in parentheses. And we want to go with the lowest number first. So we'll do 3S, comma, and then 4R. All right, we have addressing a common misconception about structures in 3D. So let me see if I can get this. Sometimes, oh, there it goes. So what we see here is that they've drawn the chlorine coming out of the page, but on the right-hand side, the hydrogen going back into the page, but on the left-hand side. So is it any different if I draw the chlorine coming out of the page to the left and the hydrogen going back into the right? So these are really the same thing. And they haven't switched the fluorine and methyl either, right? So the configuration does not change, right? No. But can we prove that to each other, right? We would probably want to figure out if it's R or S and make sure that it's still R or S, right? So let's go ahead and prove that it doesn't actually change it just by which direction you draw the dash or the wedge. We can do that by assigning the configuration. So we have chlorine, followed by fluorine, followed by carbon. And lastly, priority 4 is the hydrogen. The hydrogen is pointing straight back, so 1 to 2 to 3, right, which is counterclockwise, is S. Let's go ahead and see if it had changed over here. So same priorities, 1, 2, 3, 4. And again, I would still have 1, 2, 3. You can see that the rotation is the same direction. So nope, it doesn't change it. Either way, it's the same structure. We know that because it has the same configuration. All right, and then this just talks about what if you're given the structure in a Newman projection? Well, remember that we can go from a dash wedge notation into a Newman projection, so the opposite must also be true. We should be able to go back from a Newman projection into the dash wedge representation. So we're showing you how to do this, like put a pin in it and then rotate it to the left. And if you rotate this to the left, what we'll see is that the carbon backbone, which is the methyl carbon carbon ethyl, right, is now drawn in a zigzag here. And then the bromine and hydrogen are on a wedge and dash, and the chlorine and hydrogen on the back carbon are also on a wedge and dash. We're able to go back to the dash wedge from a Newman projection, and that could be helpful as well. So the last question says, assign R and S configurations on all asymmetric centers in the following molecule. Once you have assigned all the configurations, determine the relationship between each of the two molecules. All right, let's go ahead and work on that. So the configuration here, we have priority 1 is the sulfur. Priority 2 is going to be that carbon, followed by the methyl, followed by the hydrogen. So 1 to 2 to 3 is clockwise and R. Over here, we can do 1, again 2, 3 with the hydrogen pointing back. So 1 to 2 to 3, in this case is counterclockwise and S. Let's do the same analysis over here. So 1, 2, 3, hydrogen coming out at you now. Remember, with the hydrogen coming out at you, the fastest trick, so you don't have to redraw it, is just to do 1 to 2 to 3, and then if it's clockwise, write S. And if it was counterclockwise, I would have written R. So the next one, we have sulfur, same priorities, but now the hydrogen is coming out at us again. So again, I can do 1 to 2 to 3, which is counterclockwise. Normally I would write S, but the hydrogen is coming out at me, so I'm going to write R. So with exactly opposite configurations at each carbon, R and S became S and R. We now know the relationship between these two compounds is enantiomers, which we may have realized already because all they've done is switch what's on the dash and the wedge at each of the two chiral centers. And when you do that, as you know, you generate the enantiomer at that chiral center. But you would have to have the exact opposite at all chiral centers for the two structures to be mirror images and related as enantiomers. For this next one, it's helpful if we get it out of the Newman projection and back into the dash wedge rotation. It showed you how to do that on this exact molecule on the previous page. But we could go back. Remember, we're going to rotate this whole thing to the left. That's going to give us this carbon backbone. And then we have the bromine coming out at us, which means the hydrogen is pointed back. You can draw that in. And then the chlorine is also going to be on the same side as the bromine coming out of us. And the hydrogen pointed back. So now we can figure out the configuration at the chiral centers here. So in terms of priorities, we have 1, 2, 3, 4. With the hydrogen pointed back, we can just do a counterclockwise is S analysis. And then for this side, we have the chlorine, 2, 3, and 4. Again, the hydrogen is pointed back, so 1 to 2 to 3. And this is also counterclockwise and S. Let's come over here and see what we get for this structure. If it helps you, you can draw in the hydrogen pointed back at each of these carbons. We want to do an analysis, of course, of the priority groups. So 1, 2, 3. Fourth priority is the hydrogen. So again, clockwise is R because the hydrogen is pointed back. And then over here we have bromine followed by the carbon with the chlorine, followed by the methyl. This is clockwise and also R. So again, SS, the same groups attached as this one. This one is RR. We know those are related and as enantiomers. Looking at the next one, we want to recognize that really all that matters is the fourth priority group here is pointed out at us. And over here, it's going to be pointed back. So then we can do our analysis of priority. So 1, 2, 3, 4. Right? So we have 1 to 2 to 3. That looks like a counterclockwise rotation. Except for my fourth priority is coming out at me. This is R. And then over here, priorities are 1, 2, 3, 4. If my fourth priority group pointed back, I can just do a clockwise is R relationship. So notice that they're the same groups, OH, methyl, chlorine, hydrogen, same over here. So then these are related as identical. They're identical structures. We know that because the configuration is the same. All right, so moving on to this one. Again, it's that hydrogen group. It's either coming out at you, right, or going back. And in all cases, it's on the horizontal, so it's coming out, which will mean clockwise is really going to be S, counterclockwise will be R. So in terms of the priority groups, it's going to be oxygen, and then this carbon, this is a tie, right? Carbon and carbon, but this one has oxygen, hydrogen, hydrogen. This one has oxygen, carbon, hydrogen. This will be priority 1, priority 2, and priority 3. So again, that looks clockwise, but the hydrogen's coming out of this. So that's really S. And then over here, we can do same thing, 1, 2, 3. So we have a counterclockwise, but our hydrogen is coming out at us. So it's really R, the second carbon. Coming over here, we can do 1, 2, 3. right? 1 to 2 to 3, this is counterclockwise, but again, my hydrogen is coming out at me. It should be really clockwise and R. And on the bottom here, we have the oxygen is first priority, this carbon, and then this carbon. So 1, 2, 3. That looks like clockwise, but again, we switch it, so this is S. You can see that by switching the OH and the hydrogen, not surprisingly, we have switched the configuration from S to R and from R to S, which means that these are enantiomers. All right, that's the end of worksheet 9. See you guys next time.